Good afternoon. We're in the St. Mary's Freshman again. We're going to move on with our chemical reactions unit. In this lecture, we're going to be talking about specifically acids and bases. Things that we're going to be trying to achieve here are going to be talking about characteristics of acids and bases, being able to identify acids and bases, being able to identify types of solutions as far as acidic, basic, or neutral, and then finally being able to identify what the pH scale is and how to identify where an acid, a base, or a neutral item would be found on that pH scale. Okay, so some simple objectives here. All right, first of all, we have three definitions for an acid-base definition. The first one is the Arrhenius definition, started back in the 1880s. Then we have the Bronsted-Lowry definition. And finally, we have the Lewis definition. Lewis definition is probably the most broad, but all three really say about the same thing as far as acids and bases. If you would put their definition up against a chemical formula, the same chemical formula, you would see that they would all be speaking the same language. It's all just exactly how they want to identify what an acid base is. And the one that we're mostly concerned about and the one that we're going to use is the Bronsted-Lowry definition of what an acid base is. So, what is the definition used by Bronsted and Lowry? Well, they said that a acid was anything that has or that is a proton donor. So a proton is anything like I have down here at the bottom is basically just a hydrogen atom, okay, that has lost its valence electron. So we have a picture over here of a hydrogen atom. If it loses this valence electron, it would just be a proton. That's really all it would be. So hydrogen basically is a good way to talk about a acid or a base. Okay, so bases, if an acid is a proton donor, a base would be a proton acceptor. So again, a proton is really just a hydrogen atom that has lost its valence electron. It's a charged particle. Okay, so now in this picture here, we're going to be talking about the Bronsted-Lowry definition of an acid and base. We're going to bring up a couple of chemical formulas, and underneath those chemical formulas, I'm going to have identified the acid and the base for each one, and then you'll see something on the right about a conjugated acid and a conjugated base. That's just talking about how it's changed and how it's added a chemical. Okay, so again, an acid is a proton donor or hydrogen donor, and a base is a proton acceptor. Okay. So when we bring this up here first, okay, oh, sorry, I didn't do my clicks, okay. So here is the initial chemical equation. We have hydrochloric acid and water react to form hydronium here and chlorine ion, charged chlorine ion, and this one's charged as well. Okay, so let's talk about what this is doing here. The reason why hydrochloric acid is, considered an acid is because, according to the Bronsted-Lowry, it will donate its hydrogen or its proton, okay, and it does that and it donates it to water, okay. So this hydrogen atom is donating, is being donated here to water. So since water is, accepting that hydrogen atom, it is the base, okay. So this acid is the donor. It's donating its hydrogen to water. That makes water the base. Okay, again, protons have to be the acceptor, or the base has to be the proton acceptor. So here's your base. It's accepting the proton. And here's the final product, if you will, hydronium, H3O. We're going to come back to that molecule. So kind of keep that in your mind. H3O is hydronium. Okay. And then, of course, if this was a hydrogen, this just becomes chlorine, and this would become an electrolyte. Okay, this solution would become an electrolyte, or this particular particle would become an electrolyte, and it would have the ability to carry an electrical charge. Okay, so we'll move on to the next one here, and we'll kind of come down here, and now we have ammonia, excuse me, and water, and then we make ammonium and hydroxide ion here. So now water was a base in the previous equation, if you remember from up here. Now water is the acid. Well, why is water the acid? Well, it turns out that water is going to donate to ammonia. Okay, so what's it going to donate? Well, it's going to donate one of its hydrogens. Again, An acid is a proton donor. Okay, so we're donating that hydrogen atom, and the base is that proton acceptor. So that makes ammonia here the acceptor, and proton the donor, or the water the donor here. Okay, so in the end, you have the conjugated base here, or the conjugated acid, excuse me, as ammonium. Okay, it is a charged particle, has one more proton than it's supposed to, so it technically is a positive charge. And since OH has lost a positive charge, it has more negatives than positives, thus making it negative. Okay, so a conjugated base, conjugated acid, again, is just something that's accepted something or another element or another atom, so it's changed its particular chemical formula. So conjugated acid, conjugated base. All right, so that's kind of the basic rundown of how the formula would look. Again, the idea: an acid is a proton donor, a base is a proton acceptor. So whenever you see something, a hydrogen being donated, okay, that would be the acid. Whenever you see a hydrogen being accepted, that would be the base. Okay, so we'll move this out of the way here quick. Here are some characteristics of acids. Okay, any chemical that donates a hydrogen ion is considered an acid. Now, again, those other two definitions would talk specifically about something a little bit different as far as what an acid is, but it's all speaking the same language. Okay, so we have sour taste, generally speaking, is a good characteristic of an acid. So if you think of sour Skittles, it has an acid on it, so that makes it taste very sour. So we're talking about vinegar as a solution of acetic acid. So whenever we do our labs here, we'll have acetic acid. We're talking about vinegar. Citrus fruits also contain citric acid. Okay, a little bit less than vinegar, but it kind of depends on the concentration. Okay, they react to certain metals to produce hydrogen gas, and they also react with carbonates. So we're talking about like sodium carbonate and sodium bicarbonate to produce carbon dioxide gas. So when you watch carbon dioxide being produced, you're generally talking about carbonates. Okay, so now with that in mind. Okay, some additional things that we're going to bring up about acids, which are going to kind of help us later. Again, they create electrolytes. They can carry an electric charge. Okay, so for the most part, if you would stick some copper wiring down there with a battery, you carry electrons through a circuit. The solutions that those acids would be in would be able to create an electric charge going across that solution. Okay, something else that we're going to talk about a little bit later is the pH scale. For the most part, acids are less than 7. Okay, some science textbooks will talk about how what actually is neutral or whatnot. They'll say something like 6.5 or whatnot. But for the most part, just remember anything less than 7 is an acid. All right. The biggest thing is when we get to testing these things, we're going to talk about blue versus red litmus paper and also pH paper. The biggest characteristic about acids is that they will turn blue litmus paper to red. So blue litmus paper will turn to red in the presence of an acid. So here's a good example, or a good way to remember that. Blue to red is an acid. Okay, blue to red is an acid. So that's kind of a nice way to rhythmically think about how to figure out the litmus papers. Okay, so now we'll talk about some characteristics here. Or not some characteristics, some actual ideas. These are the actual chemical formulas and the actual chemical structure, what we're talking about. For the most part, oranges and lemons come from a very weak acid, citric acid, and then of course we have over here the ant. The sting of ants is due to the weak acid of formic acid, HCO2H. Okay. Now, we also have Bayer. I don't know, sometimes you might have a grandparent, or maybe even some of you might have a parent that has a heart condition. They a lot of times will take Bayer aspirin to help with that. But aspirin is another weak acid, has been used as an analgesic for over 100 years, and analgesic is kind of talking about pain relief. Okay. Amino acids over here, glycerin represents the amino acid that are the basis of all proteins. We'll talk about that next year, but any kind of amino acid is basically a building block. Okay, so we have acids and bases that are actually in this particular group. Okay, the CO2H group is the acetic portion of the molecule. Okay, so that's referring to this portion right here. So this is the acid portion. This will donate a hydrogen atom very easily, and NH2 group is a basic portion. So this side would accept another hydrogen if it could. Okay, so let's talk bases then. Any chemical that can accept a hydrogen ion or a proton, they generally have a bitter taste. They generally feel slippery when wet. So if you think about things that feel slippery in your mind, it should immediately take you to soap, oils, lipids, fats, anything like that is generally speaking a base. So now, a couple of other things, they actually will produce an electric charge as well. Their pH is greater than 7, so acids is less. pH for bases is more. And again, they turn their litmus paper to blue. Basic is blue. Basic is blue. Basic is blue. Okay? Some common bases. Here's a decent table of them. Something that, generally speaking, you might have in your fridge would be sodium bicarbonate. That's a decent base. But here are some other things, generally speaking, when you make lye or for soap. Okay, you have these two materials, potassium hydroxide or sodium hydroxide. I don't know if any of you are into making plastics or anything like that, but here's barium hydroxide, which is a good stabilizer for most plastics. Milk of magnesia, magnesium hydroxide, of course, Maalox, and a decent antacid is aluminum hydroxide. Okay, so here's a couple of decent bases. Caffeine is a well-known stimulant, and it's a weak base. Okay, and a sea slug excretes a strong acid. Sorry, I didn't take that picture out there, but that should have been up for the acids. Okay, but anyway, so for those of you that are getting into the coffee world, they're actually drinking a little bit of a base. Okay, so now we're going to move on to the idea, since we've identified some characteristics of acids and how to identify them within our equation. Here's another example. Okay, hydrochloric acid and sodium hydroxide. Again, this is the material that you could use for lye. Okay, but a salt. Whenever we talk about the term salt, generally speaking, you're referring to table salt, which is sodium chloride. Okay, you see that right over here. But actually salts, there's many different types of salts in the world, especially in the world of chemistry. And so when we refer to a salt, we're referring to any ionic compound formed from an acid and a base. So now a quick review. An ionic compound is something that has a metal and a non-metal bonded together with opposite charges. Okay, so in this case, we have an acid. Remember, this is an acid because there's a hydrogen peroxide, or not hydrogen peroxide, a hydrogen donor. And sodium hydroxide here is a base because it is, well, this is saying an OH donor, but generally speaking, it's going to take on this hydrogen. Okay, so for the most part, when we're talking about these acids and bases, you're talking about something that's going to create a water, you're going to create a salt. So if we have a base, it's donating a hydroxide, and an H+, which is donating a hydrogen. Okay, so for the most part, we're creating ourselves a new insoluble solid, sodium chloride, okay, from this solution. Okay, so again, ionic compounds are metals, and nonmetals are bonded together with opposite charges. Here's your ionic compound, following the cursor. Here is the water that is produced from this this current reaction. Okay, so now we'll talk about solutions here a little bit. Solutions have two parts. They're either solvents or they're solutes. Okay, solvents are the liquids that do the dissolving. Solutes are the solids that are dissolved. Okay, three basic types of solutions: either they're acidic, basic, or neutral. Now, what does that mean? Well, basically, you're going to be determining your type of solution based on hydroxide ions or hydronium ions. Okay, hydroxides are OH, hydronium ions are H3O. Okay, so you measure the amount of each of those things in the particular reaction, and that should tell you what type of solution you have. Okay, so in this case, if we wanted to have a neutral atom, okay, I'll give you a little bit better view there, equal amounts of hydroxide and hydronium ions are in the solution. So again, we have a decent graphic that I came up, well, I didn't come up with, I showed out of the book and kind of modeled it after, which I thought was really good. On the right here we have the pH scale. We'll get to that in just a little bit, but you can see there's three different parts here. Up top there is the term basic. In the middle we have the term neutral. Down here we have the term acidic. Okay, so now this is supposed to be a balance. Think about mass, okay, so the amount, so on and so forth. We have a couple of different graphics up here. Remember, hydroxide is the OH, hydronium is the H3O. In this picture we're trying to show that the balance, that these two chemicals are balanced between there, and so that they are equal to each other. So that's what this graphic is supposed to show. When they're equal, they are neutral. Okay. So that's fairly straightforward. Neutral atom would have equal amounts. So one thing that the book really shows, and one thing I want to stress to you, just because it's neutral doesn't mean that it does not have those things. Even pure water has high amounts of hydroxide and hydronium ions, but it's neutral because these things are equal to each other. Okay? So now, when we're talking about a basic solution, you're talking about higher amounts of hydroxide ions than hydronium ions in the solution. Okay? Hydroxide ions are more, the scale is going to go down. Hydronium ions are a little bit less, it's going to tilt upwards. So just like a mass scale, the heavier object is going to go down. Now I have this kind of set up so that the arrow is pointing towards the basic side, which makes sense. Okay? The more hydroxide ions you have, the more basic it's going to be. Okay, so again, here's another graphic. Hydroxide ions are greater than hydronium ions. So that's a basic solution. Now, an acetic or acidic solution would obviously have more hydronium ions in the solution than hydroxide ions. So again, the graphic is showing that we have more hydroxide ions are greater than hydronium ions are greater than hydroxide ions. So in this case, the scale is going to tilt down because this is larger than this. So if this is more, the scale should be pointing down towards acetic or acidic. Okay, so however you want to pronounce it. So this is kind of the basic plan for determining if it's a acidic solution, a basic solution, or a neutral solution. Okay, so just kind of keep that in mind. You're talking about the concentration of each type, either hydronium ions, H3O, or hydroxide ions, which are OH. Okay, so now, what does this really mean, and what is the pH? Well, the pH scale is fairly simple. The pH scale is a way of expressing the strength of acids and bases. Instead of using very small numbers, we just use the negative power of 10. Okay, so now this is going to go into a little bit deeper than what we really need to. Okay, but the basic premise is that each of these is in a certain concentration, if you will, for hydrogen ions. Okay, and there is a reverse scale for hydroxide ions. But for the most part, we're talking about the concentration of hydrogen ions. So these are all the moles, the amount of each one of hydrogen ions in there. So you can see the -7 is here at the pH scale of 7 here. A -14 is a is a 14 on the pH scale. And when you have small amounts of hydroxide and high amounts of hydrogen ions or hydronium ions, we're talking about something very, very acidic. So 1 molar HCl would be something that is extremely acidic. Okay, something that has lots of hydronium ions running around in it versus how much hydroxide ions you have running around in it. So the basic thing about the pH scale that you guys need to take away from, whether you're going to be a farmer, a pharmacist, a school teacher, a mother of 4, whatever, a father of 15, whatever you want to do, you have to understand the pH scale is there for really the safety of you, so you know how corrosive or how simple a solution really is. So the biggest things to keep in mind, again, if you're under 7 is right down here, you're acidic. Okay? If you're neutral, you're right around 7. So you're talking about milk, pure blood, and pure water. So now the stuff that comes out of the tap and the stuff that's just sitting in a lake is not pure water. Okay? We're talking about pure water that has no carbon dioxide in it. Okay? Carbon dioxide actually pushes things to be more acidic. So the type of water that you would get is something that's probably more in this range. Okay, probably something between 5 and 6. This is where the water you usually get has lots more carbon dioxide that has, dissolved into it. Pop is a good example of something that is, very acidic because of, how much carbon dioxide it has in it amongst other acids. Okay, and then something that's basic is obviously more than 7. Okay, something that's up here. So you're talking about ammonium. Ammonia, is something that is extremely basic, and it can be used for a lot of different things. Sodium hydroxide is another one that can be used to actually clear out drains, which I probably should do in my room every once in a while. But that's the basic premise. Okay, so now here's a pH scale that's showing other substances. So here's vinegar for those of you that have parents or grandparents, or even you that might drink a little bit of vinegar every once in a while. Okay, you're drinking something that's a little bit more acidic, and the premise behind that is the more acidic your blood is, the tougher it is for fungus and bacteria to grow in there. but there's a fine line. If you're too acidic, the buffering in your system won't be able to compensate, and you could die. So just be careful with how acidic you're trying to make your blood when you do those things. Blood, obviously, with the buffers or whatnot, tries to keep itself around 7.4. Then here are some heavy cleaners, ammonia, and even your oven cleaner if you spray that in there. Okay, so again, the pH scale, 14 is basic, 7 is neutral, 0 would be acidic, and anything less than that is acidic, anything more than that is basic. Okay, so pH testing is the last thing we'll kind of talk about. Remember we talked about earlier as far as the characteristic of acids, blue litmus paper will turn red, so that would be an acid. A red litmus paper turning blue, that is basic. Okay, then we have some pH paper. We'll talk about there in just a little bit. It's multicolored, so it kind of measures how basic or how acidic it is based on the pH scale. pH meters can be digital. It can be also kind of like an odometer type deal. We just have a needle that goes back and forth telling you how acidic something is based on charge. So a pH meter will actually send an electric charge through a solution or through the soil and see how it's able to conduct electricity. And it can measure, if it conducts electricity very well, more acidic it is. The less well, it's more neutral. Okay. Universal indicator solutions, more of a chemistry type deal, but for the most part, indicators like phenolphthalein would be another one which we'll use. And then the natural indicators, you could have red cabbage or radishes can be used as indicators as well. So that's kind of a neat deal. So anyway, here's what we're looking at. Red litmus paper, when we get to our lab here, red litmus paper will be turning blue, and blue litmus paper will be turning red. This is an acid, this is a base. You'll see these in the lab as well. pH hydron paper. Notice here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or sorry, 10 and then 11. So you can have the papers that go up to 12 and 14 if you want to. But for the most part, what you're seeing here is the pH scale. Okay, so here's your neutral. Okay, here's your acidic, and here's your basic. Okay. All right. So that's basically what we're going to talk about. Here's a good example of a pH meter. Again, it's sending electric charge through here, and it's coming back, and it's getting a reading of how much hydrogen it would have. Here are some more indicators. Okay, some decent pictures of what we're talking about as far as the pH is concerned and what colors that they can have. Well, that's the basic premise. So, thank you very much. Make sure you get the worksheets done. Thanks.